Greetings, Mathophiles. Welcome to a video in which we'll take a look, start to finish, at a max-min or optimization example from calculus. And we'll dive right in. It goes like this. A truck gets 400 over R miles per gallon when driven at a constant speed of R miles per hour, where R is on the closed interval 50 to 70. I don't know whether this is strictly speaking, a realistic function form, but I know that there is a lot of evidence that vehicles of all kinds over this interval tend to get worse mileage the faster they go. And this at least captures that since it's a decreasing function. If fuel costs $4.40 a gallon and the driver earns $36 an hour, at what speed R, unclosed 50 to 70, is the cost of operating the truck minimized? So the tension is between the cost of the driver and the cost of the fuel, right? If the driver is going faster, they're going to get there sooner. It's going to cost less in terms of their hourly wage, but it also is going to contain a cost in terms of the gas mileage, which translates into the money that the trucking firm has to pay to keep the rig on the road, so to speak. This problem, I should note, is adapted from one posed by Luke Lang on the College Board AP Calculus teacher mailing list a long time ago, sometime in the aughts. And I have updated the numbers to reflect current reality a little bit more accurately. So here is the bare bones information. The mileage of the truck is 400 over R miles per gallon. The driver is making $36 an hour. Fuel is $4.40 a gallon. And we want to minimize the cost per mile. It's good to take note of what our units are. They are miles, gallons, dollars, and hours, respectively. We don't lose anything, and we gain a little bit of convenience if we just try to figure out the minimum cost of going 1 mile. So let's assume that the distance involved is a constant 1 mile. And let's think about the cost first of the driver. So one of the more useful things you learn as a student is that distance equals rate times time if you are dealing with a situation in which there's a constant rate. And so let's assume that the distance is 1 mile. And then what is the time that it takes the driver to drive the 1 mile at a given rate? It is 1 over R. All right. And that would be in hours. So how about the cost of the driver then for that time? It's going to be $36 an hour times the 1 over R hours. So the driver cost is 36 over R dollars. And if you have any doubts about how those units set up, you can go back and double check that they all are operating and canceling exactly as one would hope and expect. How about the fuel cost to go 1 mile? Well, we're paying $4.40 a gallon. And if we have 400 miles per gallon, then we have R over 400 gallons per mile. And what's this going to be? This is going to be 440 R over 400, and this is going to be dollars per mile. And if you wanted to reduce that fraction, you certainly could, and you would get 11R over 1,000, and that is again in dollars per mile. So the cost to drive this truck 1 mile should be the sum of the driver cost and the fuel cost. And so on the next page, we'll proceed on that basis. So I've carried over onto this page the key information, the cost of the driver being 36 over R and the cost of the fuel being 11R over 1,000. And so the total cost to run this truck as a function of the rate at which it's being driven is just the sum of these two. So it is 36 over R plus 11R over 1,000. And we're going to minimize the cost of operating this truck either at an endpoint of our interval from 50 to 70 or at a critical value. So we need to go looking for those. So C prime of R is negative 36 over R squared plus 11 over 1,000. If we set that equal to 0, we find that there's one moment on the interval where the derivative is 0, and that is at about 57.2 miles an hour. So there are three places we have to consider, three different rates that we have to consider as candidates for the location of the minimum cost per mile. So here's R, here is C of R, and we need to take a look at 50 and 70, and we now know 57.2. So you all know arithmetic. I won't go through the motions on this. I'll just tell you what these numbers are. We plug these R's up into this cost function. We get that at 50 miles an hour, it's about $1.27 per mile. At 57.2 miles an hour, it's about $1.26, 259. And at 70 miles an hour, it's about $1.28. So there's not a huge difference here, right? It's only about 2.5 cents between the optimum and the maximum speed that we've considered, which is 70. So is this a lot of money? Is it really worth bothering about this even? Well, if you assume a driver drives 8 hours at 60 miles an hour, then they've gone in a day about 480 miles. And over a work year of, let's say, 250 days, if you do a few multiplications, you find that over the course of a year, it's about $3,000. Not to be sneezed at, I'm not an expert, but I think that the trucking business is fairly competitive. And so additional economies maybe are very useful to be able to find. You could make this problem a little more realistic maybe by making some assumptions about obligations to deliver material in a timely fashion. Suppose you had an additional requirement that the load had to go 275 miles and it had to get there in 4 hours. That would put you on a different interval, potentially give you a different answer. So as you are well aware, if you're watching this video, we tend to make some simplifying assumptions for the sake of the exercise and for the sake of the understanding that we get from working through these problems. So I hope this has been helpful for you to see. Happy mathing.